2, 1, let's go. Alright, operational properties, part 2. Moving right along in chapter 7 here. Alright, so, goal for today, following up our last video, we're building up some more tools, some more facts about the Laplace transform. We're getting our toolbox more advanced to help us out with dealing with the Laplace transform, right? Because as we've already discussed, every differential equation turns into a inverse Laplace transform. Well, almost every one, right? The linear ones we can turn into inverse Laplace problems. And as we saw, the inverse Laplace problem itself can be very tricky. So we want to build up some maneuvers to help us out with inverse Laplaces. So that would then help us solve differential equations. All right, so the reason, again, all of that goes down is because the Laplace transform of a derivative turns out like this. We get s times the Laplace transform of our function minus f evaluated 0. So the Laplace transform removes derivatives. We like that because we've got equations with derivatives that we don't want to have derivatives in them anymore. All right. Let's flip this. Instead of finding the Laplace transform of a derivative, let's find the derivative of a Laplace transform. Now, bear with me. I'm going somewhere with this. All right, so set that up. If we're going to take the derivative of the Laplace transform, it's going to be derivative of that integral right there. Now, as I've already said, you can pull that derivative in. Completely legal, completely fine. Now, what's going to happen with that derivative? That derivative is with respect to s, not with respect to t. So my f of t doesn't care. It goes along for the ride. And my e to the negative st, well, the derivative of s, that's going to spit out a negative t by the chain rule. And here now, if we clean it up, pull out a minus sign and group the terms together, oh, wait a minute, this looks real familiar. And it should, because that's simply the Laplace transform of t times f of t. All right. Neat. So, the derivative of the Laplace transform, we actually now have a nice formula for it. It's negative Laplace transform of t times f of t. All right. Now, that shouldn't be too surprising, right? When we talked about the Laplace transform of t, I basically did this exact same move, so. Derivative of Laplace transform, maybe somewhere in your mind you're thinking that t is going to show up to the party. It does. And when it comes to this formula, as we're going to see, its real power is going to be using it in reverse, rather than actually going, hey, let me take the derivative of the Laplace transform. Really, I'm going to want to look at the Laplace transform of t times something, and then use this derivative information to help me. Speaking of derivatives, the best part about them is that, well, you just can't have one. Let's take another derivative. Right, so if I want to do the second derivative, well, I know what the first derivative is. It's going to be negative Laplace transform of t times f of t. The second derivative is just do the derivative twice. Derivative's linear, so I can pull out the minus sign. And as we just learned, if I want to take the derivative of a Laplace transform, it's negative the Laplace transform of the function inside times t. So my function here is t times f of t. So, parentheses galore, we get this. And this is pretty atrocious looking, so let's clean it up. And oh, look, it cleans up pretty nicely. All right. So, nothing's stopping us from doing this a third, a fourth, a fifth, a sixth, a seventh, an eighth, and so on and so forth. So, in fact, you can verify that the nth derivative of a Laplace transform will satisfy this. Okay, and now note, I rewrote it in a different way. I rewrote it specifically saying that t to the n times f of t, that behaves nicely, right? And in some sense, this is really how we're going to use those in new information. We're really going to be focusing more on, well, if I've got Laplace transform with t times something, I know it involves taking derivatives. So that's how it's going to be applied, but how we're going to use it, like I've already noted, is going to be backwards. So let's use this forwards first for sine and cosine. So if I want to look at the Laplace transform of t times cosine of kt, all right, well, we know that if you want to do the Laplace transform of t times something, it's the negative derivative of the Laplace transform of the term without t. Laplace transform of cosine, I know what that is. It's sine over s squared plus k squared. That gives me that. And I just want to take the derivative of that. That is a quotient rule. And note, I have the minus sign here. So when I do the quotient rule, I should have gotten k squared minus s squared at the top, but that minus sign flips the order. So we get this nice, appeasing looking function right there. And you can do the same thing for sine, and for sine it works a little bit easier because, well, it's just a k up in the top. So the quotient rule cleans up nice. And again, there is a minus sign, so instead of a negative 2ks in the top, we will get a just 2ks. Nice. And, ooh, caught a typo. That needs to be k squared down there. Let's fix that. And by the magic of mathematics, we got it. Okay. Nice. Not too bad. And I was able to edit it on the fly without everything crashing. So that's good. Alright. Now, like I said, we are going to apply it forward, but we're really going to use this backwards because this now tells me, and good thing I've got it right there, so no copy pasta. This tells me that there are now certain inverse Laplaces that I can quickly do. Right, and t times cosine and t times sine, we saw those when we were solving non-homogeneous second-order linear constant coefficient differential equations. We saw these things. So having these in your back pocket and ready to go is going to be a useful technique, right? Because irreducible quadratics being squared, or you'll run afoul of those. And trying to directly handle that without these ready to go, not a good time. So these are definitely good things to have at the ready. So some good stuff when it comes to doing certain inverse Laplace problems that can get a little sticky. All right. That being said, we haven't done a differential equation in a while, so this is differential equations. So let's look at one. There we go. That, on its face value, doesn't look too awful, and in fact, you could solve this using the previous techniques, but let's use the Laplace transform. Okay, so on the left-hand side, the Laplace transform of that is this. Note that this is the second derivative, which is really just the derivative of a derivative. So that turns into this, and I'm going easy on us, so that's going to zero out. The y prime will disappear. Apply that same rule again. And then we'll have s times all that junk, but y0 is 0, so that drops out again. Convenient. And leaves me with an s squared times the Laplace transform of y plus the Laplace transform of y. Minding my p's and my q's, I can clean that up and I get this, and I see that I've got s squared plus 1 times the Laplace transform of y, and as I've noted, hey, that's the auxiliary equation. If you get to the point here, and after the factoring, you do not have the auxiliary equation times the Laplace transform, something has gone awry. All right, but it lined up, so as far as I know, I'm doing everything right. Okay. Now, what will we do next? Well, now we would combine this with the Laplace transform of the right-hand side. So specifically, we would then have s squared plus 1 Laplace transform of y coinciding with the Laplace transform of t. Now, what we did before was actually take the Laplace transform of t, right, which is 1 over s squared. Now, you could do that. Divide over the s squared plus 1 and then have a partial fractions that you'd have to deal with. Or we can look at it in a different light. So rather than actually taking the Laplace transform of t, let's do the other thing. Move the 1 over s squared plus 1 to the right-hand side. 1 over s squared plus 1 conveniently is the Laplace transform I know. I know that it's the Laplace transform of sine. So solving this differential equation is equivalent to this Laplace problem. Specifically, find the Laplace transform that gives me the product of the Laplace transforms of sine of t and t. All right, well, the first thing that I want to stress is that we do not have the following formula. The Laplace transform of a product is not the Laplace transform, the product of the Laplace transforms. Right, just in the same way that the derivative of a product is not the product of the derivatives, this is not going to fly. Right, we need a product rule to get the derivative of a product. Right, and the same deal with the integral of a product. We know that in general that's not the product of the integrals. That does not happen. So, right, and as we've even seen, the Laplace transform itself is an integral of a product, and we've had to go through all sorts of hoops and songs and dances and illegal maneuvers to get that to work out for us. So, no hope of this being true. But it does turn out that you can find a function that does have this property. Right, it turns out that the Laplace transform has this really neat product formula. Specifically, the product of Laplace transforms does turn into a Laplace transform of something. The problem is the something that you need here is a little convoluted. All right, so here it is. The thing we're looking for is going to be the convolution. All right. Now, let's digest this, let's read it, and let's think about it. It's, again, another integral defined function. And note how it works. You feed me an input t, and I do the integral from 0 to t. And what I'm going to do is put in this dummy variable, this new variable tau, and integrate against that. So tau is going to run from 0 to t, and we're going to go ahead and do this. Note the inputs add up to t. So that's a fact that we can use to help us out. All right, now if you've done any signal processing, you've definitely ran into this. If you're going to do some signal processing, I'm sorry, you're going to have to deal with this. So before we start getting the Laplace transform into the party, let's get a flavor for how this works. Let's do the convolution of sine of t and t. For no particular reason on that one. Let's just do that one, right? Because I'm not trying to figure out, anyway. All right. So that means you're faced with this integral, right? Replace f with sine, replace g with just t. Right. Note t minus tau. So respecting all my operations. All right. Now, I wish I had a trick for you. I wish I had a slick way of doing this integral. I don't. You just got to do it by parts. And I'm sorry. But don't worry, I promise. I'm going to blow your mind in a little bit with an integral maneuver. But for this one, this just, not integrate by parts. I don't know of any other way of doing this one, so set it up. We'll let the thing we're going to take the derivative of, let's pick t minus tau. That seems pretty easy. Note again, we want d tau, not dt. And we'll let v be sine then, the leftover stuff. Integrate with respect to tau, right? So we've got two variables running around again, so when you're dealing with these, you got to be really careful about how you do them. All right, but, you just integrate by parts, and honestly, comes out real easy, right? So the integral from 0 to t will be u times v evaluated from 0 to t. When you plug in t, hey, t minus t, that's 0. It's dead. Plug in tau equals 0, we get cosine of 0, which is 1, and a negative t, so we then pick up a positive t. And here, the integral of cosine, that gives me a sine. Now, note that, again, I got another screw-up. That should be a minus sign, not a plus. So, oh boy. All right, and then, another update on the fly. We'll do it live. Right, note that I need to be a minus sign. Negative cosine of tau times d tau is positive cosine of tau d tau. Okay. Another correction on the fly today. That's 2-in-1 video. That's a C+ right there, let me tell you. Anyway, and then the integral of cosine of tau d tau gives me, of course, sine of t. And sine of t is just t, and sine of 0 is 0, so there you go. All right, well, the convolution of sine t and t is not too bad. It's just t minus sine of t. All right. Well, as I've already revealed, the convolution and the Laplace transform behave very nicely. So, let's get nuts. I'm going to take the Laplace transform of a convolution. Let us try to take it. Alright, so if you set it up, it looks like this. And, oh boy, it's now gotten salty. Right? Look at this. Look at this. We got three variables running around. We've got s, we've got t, we've got tau. We've got two integrals running around. We've got the integral with respect to dt, we got the integral with respect to d tau. Oh boy, this is just great. Alright, well. Note that this e to the negative st, speaking of variables, in the eyes of tau, this is a constant, so I can bring that in. And, ooh, nice. Now, the thing that we want to do is interchange the order of integration. Now, we want to be really careful here, because I can't just do the thing you're thinking, which is integrate from 0 to t and then integrate from 0 to infinity. We can't do that, because the integral here, 0 to t, that depends on t. So I can't swap these. Well, I can, but I gotta be really careful about how I do it. Because I gotta think about where t and tau live. Now, t runs from 0 to infinity. So if I'm going to swap the order of integration, that's going to put a d tau on the outside. So I need to know where tau lives. Well, t runs from 0 to infinity, and tau runs from 0 to t. So that means tau would run from 0 to infinity as well. But where does t run? Well, t, as I just noted, will run from 0 to infinity, but t will always have to be bigger than tau, right? That's how this is set up in here. So if I swap the order of integration, I'll have a d tau on the outside, a dt on the inside. Tau runs from 0 to infinity. T runs from tau to infinity. Ooh. So I can swap the order, but I needed to be really careful this time because the integral on the inside depended on the outer integrand, right? The bounds depend on t. So if I swap, I gotta be really careful about those bounds of integration. Okay. Alright, now that we've done that, we've got this. That tau down there is pissing me off, so let's fix it. So we'll shift the integral so that we start at 0, and if we do that, well, f of tau doesn't get affected, so that goes along for the ride. T now, minus tau, that runs from 0 to infinity, so it just gives me t, right? Plug in tau, we have g of 0, plug in tau plus 1, we've got just 1. So this will just turn to a g of t. So t basically turns into t plus tau. Right, we shifted it. So that cleans up like that. And then now if you're looking at this f of tau I can pull out. A e to the negative s tau can be pulled out. And then on the inside, all I've got is e to the negative s t gt, so I can divorce those integrals from each other as follows. And, oh man, 3 times is the charm today, apparently. My f of tau disappeared. There it is, I got it. They come in 3s. Yeesh. Yeah, I'm now in the D- territory, which incidentally is the grade I got in physics too. Anyway, so the integrals are now decoupled, and hey, the tau is just a placeholder, a dummy variable. T is a dummy variable, it's just a placeholder, because those are really just the Laplace transform of f times the Laplace transform of g. So boom, here we go. The Laplace transform of a convolution is the product of the Laplace transforms. So now, going back to this differential equation, that's the same thing as figuring out the Laplace transform of y equaling the Laplace transform of sine of t times the Laplace transform of t, and as we just proven, that's the Laplace transform of sine of t convolved with t. So that means y has to be sine of t convolved with t, which we've already solved for. Ooh, look at that. That is devastatingly interesting. All right. Now, don't let this stop you, because now all of those inverse Laplaces that we've been doing for solving diffie q's, you can actually attack them with convolutions. And they come out really nice, because almost always on the right-hand side, you're going to have a product of Laplace transforms when you solve a diffie q using Laplace transforms. So try some convolutions out. I'm telling you, give them a go. And they may look frightening at first, but once you play around with them enough, they're actually quite useful. And as I've said, if you're going to do anything with signal processing, you're gonna learn to love them. Okay. All right. So what's next? What's next? All right. So we've got one more section to go. We've got 7.5, where we're going to talk about something. But before we move on to that, I want to sneak in something. So if you're sick of the sound of my voice, you can stop the video at this point. But I'm just going to do a little gushing right now. I'm going to talk about something that I love, and I've got some fun stories about. So I do want to stress that what I'm about to talk about is not anything that will show up on like homework exams or quizzes or anything like that. But this stuff is super cool, so stick with me. Right, it's only 4 slides. It's not that bad. All right. So let's let our minds float back. We figured out the Laplace transform of t to the n is n factorial over s to the n plus 1. Okay. This suggests that the Laplace transform of the square root of t, which is t to the 1/2 power, that means it should look something like this, but there's a bit of a problem with that formula I just wrote. Factorial of 1/2 doesn't make any sense. Right, the way factorial works is, right, you take the product of all the integers less than or equal to that given integer. Except for 0. 0 factorial we take to be 1 for reasons. A lot of valid ones, but you know, it's the anomaly. But for the most part, the way we defined it is, yeah, it's multiplying up previous terms. So 1/2 factorial doesn't make any sense. Or does it? Ooh, so let's take a closer look at the Laplace transform of a power function. So t to the r, where r could be anything. Okay. Alright, so that integral, at first glance, might be like, what do I do with this? Alright, so let's let z equal st. Okay. So let's do, maybe the thing that you've been itching to do with Laplace transform. That st is the problematic thing. So if we do that, note that z has to run between 0 and infinity because, right, t runs from 0 to infinity. Multiplying by s isn't going to change that. T itself is z over s, and dz is s times dt. So if I plug all that into the integral, that turns into this. And note, this 1 over s to the r plus 1 term, right? Oh, s to the n plus 1. Oh, ooh. So that is not unexpected. We should have expected to see this showing up. And that leaves this thing. Should probably put a little effort in to figure out what's going on with that integral. Okay. So it turns out that people have done this. And this function's been around for a really long time, right? In fact, this predates the Laplace transform itself. So this integral is a very important integral. And I can't even begin to stress how essential this function is to mathematics. So specifically, the gamma function is defined to be the following. It's the integral from 0 to infinity, e to the negative s, z to the r minus 1 dz. So note, it's another integral defined function, but note where all of the ingredients are. E to the z, negative z, right, that is getting integrated out. The input is coming from here. The input is the power on the z term here, the polynomial term. All right. So historically speaking, the Bernoullis cook this thing up. Legendre's the one who gave it the gamma symbol, and of course, has all the good things in mathematics. Euler is the one who really pushed this thing to the edge. So note that gamma of r plus 1 is actually that integral we just saw, so I now actually have a new exciting formula. The Laplace transform of a power function, so a t to a power, is actually equal to the gamma function of r plus 1 over s to the r plus 1, and now, that thing I was complaining about, hey look, r plus 1, oh, that's nice. That's beautiful. All right. So speaking of that, there is a mathematician by the name of Gauss who hated this for one reason or the other. He doesn't like that the gamma function isn't this function right here. Apparently he hated that this is gamma of r plus 1. He wanted this to be gamma of r. So he said that this thing here should be pi, the different function, but that one didn't catch on. There's actually a good argument in favor of that, and we'll kind of touch on it here, because note now, I know that the Laplace transform of t to the n is n factorial over s to the n plus 1. So this actually tells me gamma of n plus 1 is n factorial. Right. So that's the Gauss didn't like that. He wanted gamma of n to be he wants gamma of n to be n factorial, but he lost out on that one, unfortunately. There are some other reasons to debate it, but there is actually kind of a weird moment in math history where people started arguing about notation, which that's our burden as mathematicians. You're right. We got philosophy beat because we don't spend all of our time arguing about the definition of things, right? We agree with, like, what function. This is what we mean by a function. We all agree on what a function is. When we start fighting with each other is well, I use this notation. Well, I think that notation sucks. So anyway, so if we now go back, the Laplace transform of the square root of t, we now know how to compute that. It's the gamma function of 3/2 divided by s to the 3/2. All right, well, maybe gamma of 3/2 is unsatisfactory to you. Maybe you want a nice little value for that. Well, let's think about what that would have to be. Well, that'd have to be that integral right there, and that integral, of course, is square root of pi all over 2. I want to stress that is a very challenging integral. That requires some real fancy techniques to solve that. So the trick to pulling that integral off is a u substitution. You let u be square root of z. And then you get the integral of e to the negative u squared, and that is a very famous integral, and its value is known. It is spits out the square root of pi over 2. So that integral is not easy to solve. But anyway, so you get that, and there you go. Maybe that's a bit more of an appeasing answer, or maybe it's not. Square root of pi showed up because, why not? But I do want to give you a parting shot. Gamma of 3/2 is gamma of 1/2 plus 1. So like I said, 1/2 factorial doesn't make any sense. Except that it does. So we can actually call 1/2 factorial something. We can actually give it a value, right? It's square root of pi all over 2, because why not? What other value could it possibly take? Oh man, that to me has always been just the silliest math result. I mean, we've seen with complex numbers some goofy stuff that you can do. E to the I pi plus 1 is 0, and there's some other silly things you can do with powers of I and things like that. But this one is just astounding. All right. Okay. All right. So thanks for sticking with me here for the little extra fun. The gamma function for me is a very special place in my heart. undergraduate research project that I did was studying the gamma function, so its history and some of the more modern things. The gamma function is tied to something called the Riemann zeta function, and you may have heard of the Riemann hypothesis, and that's currently the big unsolved problem in mathematics. If we could crack that one, that just, oh boy, that'd be great. If you want to earn like 1,000 PhDs at once, just figure that out. There is a way of getting to that hypothesis using the gamma function, which is not easy, but it's there. But anyway, so check it out. It's a favorite function of mine. This is some cool things. Hope you enjoyed it. All right, I will see you in the next video.